Hello there and welcome to Depths of Unknown. There is a boundary in the ocean that most people have never heard of and that may be one of the most consequential ecological lines on Earth. It has no coordinates. It moves. It cannot be seen from the surface, cannot be felt by a swimmer, cannot be photographed from a satellite. It exists in the darkness, hundreds of meters below the surface of every ocean on the planet, and it marks the edge of a zone so depleted of oxygen that most complex life cannot survive there. Scientists call it the oxygen minimum zone boundary, and for the past several decades, that boundary has been moving, not drifting, not fluctuating with seasonal cycles, but expanding steadily, measurably, in a direction that carries the most profound implications for everything that lives in the ocean, for every fishery that feeds human populations from the sea, for the carbon chemistry of a planet already under enormous atmospheric stress. The ocean's dark zone is growing, and the reasons it is growing are embedded in the same set of processes that are warming the atmosphere, acidifying the surface ocean, and restructuring the biological communities of virtually every marine environment on Earth. This is the story of what oxygen minimum zones are, why they exist, why they are expanding, what lives in them and what cannot, and what their expansion means for the future of the ocean as a functioning biological system. To understand why oxygen minimum zones exist in the first place, you need to understand how oxygen gets into the ocean and how it gets used up. The surface ocean is well oxygenated, in contact with the atmosphere, stirred by wind, warmed by sunlight, and populated by photosynthetic phytoplankton that produce oxygen as a byproduct of converting light and carbon dioxide into organic matter. But oxygenated water at the surface and oxygenated water at depth are very different things. As you descend through the water column, several things happen simultaneously that create the conditions for oxygen depletion. First, the water becomes colder and denser, and cold, dense water tends to sink, carrying whatever oxygen it contains down into the depths. But this process of downwelling is not uniform or continuous everywhere, is the oxygen minimum zone, a layer of water where dissolved oxygen concentrations fall so low that most aerobic organisms cannot function. The oxygen minimum zones of the world ocean are not new. They are ancient features of the marine environment, products of the same physical and biological processes that have governed ocean chemistry for hundreds of millions of years. The major oxygen minimum zones are located in the eastern tropical Pacific, the Arabian Sea, the Bay of Bengal, and parts of the eastern Atlantic. Regions where a combination of high surface productivity, limited deep water ventilation, and specific current patterns creates the conditions for oxygen depletion in the mid-water. In these zones, dissolved oxygen concentrations can fall to near zero, to levels at which no complex aerobic life can exist, where the normal food web collapses, where the only organisms that can function are anaerobic bacteria using nitrate or sulfate as electron acceptors instead of oxygen. These zones have always been there. What is new is their size, their intensity, and the rate at which they are changing. The measurement of oxygen minimum zone expansion is not a theoretical projection. It is an empirical observation accumulated over decades of oceanographic research using ship-based measurements, autonomous profiling floats, and sediment core analysis that extends the record back thousands of years. The data shows, with high consistency across multiple independent measurement systems, that oxygen minimum zones globally have expanded by an estimated 3 to 8% since the middle of the 20th century. In the tropical Pacific, oxygen minimum zones have expanded by hundreds of thousands of square kilometers. The eastern tropical North Pacific oxygen minimum zone has been particularly well documented. Measurements taken at the same locations over decades show that the upper boundary of the oxygen minimum zone has shoaled, meaning it has moved upward toward the surface, compressing the habitable zone. Available to mid-water organisms, the lower boundary has simultaneously deepened in some regions. The zone is expanding both upward and outward, consuming habitable ocean volume from both directions. The primary driver of oxygen minimum zone expansion is ocean warming, and the mechanism is direct and physical. Warm water holds less dissolved gas than cold water. This is a fundamental property of aqueous chemistry, the same reason that a warm soda goes flat faster than a cold one. As the surface ocean warms in response to anthropogenic greenhouse gas emissions, the oxygen content of the warming water decreases. But the warming effect on ocean oxygen is not limited to the surface. Warming also affects the stratification of the water column, the degree to which surface water and deep water are separated by density differences. A warmer surface ocean is less dense relative to the cold deep water below it, which means the density gradient between surface and deep water increases, making it more difficult for the two layers to mix. This reduced mixing means that the well-oxygenated surface water mixes less efficiently with the oxygen-depleted mid-water and deep water below. Less mixing means less oxygen supply to the depths, which means the oxygen minimum zones grow. There is also a biological component to oxygen minimum zone expansion that compounds the physical warming effect. As the surface ocean warms, the distribution and productivity of phytoplankton changes. In some regions, warming increases stratification to the point where nutrient supply to the surface from deep water is reduced, decreasing phytoplankton productivity and the organic matter that sinks to the midwater to be decomposed. In other regions, warming and nutrient shifts alter which species of phytoplankton dominate the community, changing the quality and quantity of organic matter available for midwater decomposition. The biological pump, the suite of processes by which carbon fixed at the surface is transported to the deep ocean, is being restructured by warming in ways that affect oxygen consumption at depth in complex and not fully predictable ways. What the observations consistently show, despite this complexity, is that the net effect of these changes is more oxygen depletion, not less, in the mid-water zones where oxygen minimum zones already exist. The chemistry of oxygen minimum zones is not simply a matter of low oxygen. In zones where oxygen falls below certain thresholds, the chemistry of the water shifts in ways that have profound implications for marine life and for global biogeochemical cycles. When oxygen is nearly absent, anaerobic bacteria begin to use nitrate as an alternative electron acceptor for respiration, a process called denitrification that converts nitrate into nitrogen gas, which escapes to the atmosphere. This loss of nitrate, the primary nutrient for phytoplankton growth in much of the ocean, represents a reduction in the ocean's productivity potential, a feedback that can affect surface ecosystem productivity across entire ocean basins over long time periods. In the most severely depleted oxygen minimum zones, the water can become sulfidic, containing hydrogen sulfide produced by sulfate-reducing bacteria, creating conditions that are toxic to essentially all complex life and that can, in extreme cases, cause mass mortality events when the oxygen minimum zone shoals close enough to the surface to affect coastal and near-surface ecosystems. The organisms that have evolved to live in and around oxygen minimum zones represent one of the most fascinating chapters in marine biology, and understanding them matters for understanding what oxygen minimum zone expansion actually means ecologically. The boundaries of oxygen minimum zones, the upper and lower edges where oxygen transitions from habitable to uninhabitable levels, are some of the most biologically active zones in the entire ocean. Organisms from above and below concentrate at these boundaries because they represent the edge of the survivable world, and the compression of organic material at these edges creates extraordinary densities of life. Myctophid fish, the lanternfishes, are among the most abundant vertebrates on Earth in terms of total biomass, and they spend their days in or near the oxygen minimum zone, migrating upward at night to feed in the oxygen-rich surface waters and retreating downward before dawn in one of the most massive daily migrations in the animal kingdom. The oxygen minimum zone boundary is their refuge, because the low oxygen that protects them from well-oxygenated predators above also determines the limits of their world. The expansion of oxygen minimum zones has direct and measurable effects on the organisms that live in and around them, and those effects are not uniform. For organisms that are adapted to low oxygen, expansion of the oxygen minimum zone can represent an expansion of available habitat. But for the fish and marine mammals and large invertebrates that constitute the productive, commercially important components of ocean food webs, shoaling of the oxygen minimum zone boundary represents compression of the vertical space available for foraging, reproduction, and movement. Tuna, billfish, and sharks, apex predators that constitute some of the most important commercial fisheries on Earth, are highly sensitive to oxygen concentration. As the oxygen minimum zone shoals, these animals are compressed into an increasingly shallow layer of well-oxygenated water near the surface. This compression does not immediately reduce their numbers, but it concentrates them in a smaller volume of ocean, alters their behavior and physiology, and changes their vulnerability to fishing pressure in ways that have real implications for fishery sustainability. The impact of oxygen minimum zone expansion on deep-sea benthic communities, the organisms living on and in the seafloor, is another dimension of the problem that is only beginning to be understood. The seafloor below oxygen minimum zones is chemically inhospitable to most benthic organisms. As the oxygen minimum zone expands laterally and downward, it imposes hypoxic or anoxic conditions on seafloor communities that were previously oxygenated, eliminating the complex benthic ecosystems that had developed there and replacing them with bacterial mats adapted to low oxygen conditions. Oceans functioning as a biogeochemical system. The interaction between oxygen minimum zone expansion and the ocean's role in the global carbon cycle is one of the most significant and least publicly discussed consequences of this phenomenon. The ocean absorbs approximately 25 to 30% of the carbon dioxide emitted by human industrial activity each year, and the mechanisms by which it does so depend critically on the functioning of the biological pump and the chemistry of the deep water. As oxygen minimum zones expand, the denitrification that occurs within them removes nitrate from the ocean, reducing the nutrient base for surface productivity. Reduced surface productivity means a reduced biological pump. A reduced biological pump means less carbon transported from the surface to the deep ocean, which means more carbon remaining in the atmosphere. The expansion of oxygen minimum zones is therefore not only an ecological problem, but a climate feedback, a process by which ocean warming causes changes that reduce the ocean's capacity to absorb the carbon emissions that are causing the warming in the first place. The geographic distribution of oxygen minimum zone expansion is not uniform, and understanding the regional patterns matters for understanding where the effects will be felt most acutely. The eastern tropical Pacific is experiencing some of the most dramatic expansion, with direct implications for the highly productive upwelling systems off the coasts of Peru and Chile that support some of the world's most important fisheries. The Arabian Sea oxygen minimum zone is expanding in ways that threaten the productivity of one of the most biologically important ocean regions in the world. The Bay of Bengal shows a complex pattern of expansion that interacts with the freshwater input from major river systems in ways that are not yet fully understood. In each of these regions, the expansion is interacting with existing stresses, overfishing, coastal pollution, ocean acidification, to create compound effects that are more damaging than any single stressor would be alone. The scientific tools available for studying oxygen minimum zones have advanced enormously in the past 2 decades, and this advancement has produced both more precise measurements of the expansion and greater understanding of its mechanisms. The Argo Float program, a global array of approximately 4,000 autonomous profiling floats that continuously measure temperature, salinity, and oxygen throughout the world ocean, has provided a level of observational coverage that was previously impossible, and the data it produces has confirmed and refined the picture of expanding oxygen minimum zones that ship-based measurements had suggested. More recent floats equipped with biogeochemical sensors have added the ability to measure nitrate, pH, and other chemical parameters, building a more complete picture of the chemical changes occurring throughout the water column. Despite this progress, significant gaps in the observational record remain, particularly in the Southern Ocean and in the deep water below 2,000 meters, and the models used to project future oxygen minimum zone expansion carry substantial uncertainty, primarily because the biological feedbacks involved are complex and incompletely understood. What the expanding oxygen minimum zones are ultimately telling us is something that the ocean has been communicating through multiple lines of evidence for decades, that the ocean is not a passive reservoir for the consequences of atmospheric change, but an active and responsive system whose own changes feed back into the climate and ecological processes that are driving them. The ocean absorbed the heat, the ocean absorbed the carbon, and now the ocean is beginning to express the consequences of those absorptions in its chemistry, its biology, and its physical structure, in ways that are measurable, that are accelerating, and that are not reversible on any timescale relevant to human civilization. The oxygen minimum zones are expanding because the ocean is warming. The ocean is warming because of what we are putting into the atmosphere, and the expansion of those zones is reducing the ocean's capacity to absorb what we continue to put there. It is a feedback loop written in the chemistry of seawater, playing out in the darkness hundreds of meters below the surface, invisible and largely unknown to the civilization whose activities are driving it. The dark zone of the ocean is expanding. It is moving upward toward the surface and outward toward the coasts. It is compressing the habitable volume available to the animals that constitute the productive heart of marine food webs. It is altering the biogeochemistry of the deep ocean in ways that feed back into the carbon cycle and the nitrogen cycle and the productivity of the surface ocean above. It is doing all of these things measurably, documentably, consistently, in every ocean basin on Earth simultaneously, and it is doing them silently, invisibly, in the darkness where most people will never look, driven by processes that are well understood and that could, in principle, be addressed by the same changes in human energy systems and land use that would address the other consequences of the warming that is causing them. The ocean does not negotiate. It does not offer a second chance at the same set of conditions. It responds to what it receives, and it has been receiving for 70 years of accelerating industrial activity, more heat and more carbon than it was built to absorb. The dark zone is the ocean's response, and it is still expanding.